Mm. No, civil. My undergrad and master's are aerospace.
Okay, guys, you ready? All right, we have a special guest with us here today. Is this working? Yeah. All right, so up to this point, most of our presentations on the data science has been around R. So we're going to kind of switch gears a bit. So we have a special talk today from Dr. Dharhas Pothina. Dharhas started with ITL in 2014 as a research civil engineer. His undergraduate and master's degree is in aerospace, and his PhD is in civil engineering from the University of Texas. And I don't hold that against him, so I'll let him have that. He started with ITL in 2014, and this past January, perhaps, he became our ATD. So he's a ATD for computational science and engineering in ITL. Okay. In terms of his write-up here, he's done a lot of coding. He's kind of a hydroinformatics guy. He has the same type of background as like Rob, the group over in CHL, so we pulled him out of there. He's got C++, Fortran, Perl, Matlab, Python, nice background in modeling. He contributes to the scientific Python libraries, and he's on the organizing committee for the annual Python Scientific Computing SciPy Conference. So he, Dharhas lives in Austin. We have 2 ITL employees in the Austin area. He's one of them, so he's a good connection over into the Austin space. That's kind of the center of the universe for Python development, so he's a good connection if you need to go over there and talk with some of the leading companies in Python. So with that, I'll turn it over to Dharhas.
Thank you. Afternoon, everyone. Thought I'd give a... Am I echoing? I thought I'd give you a kind of background of my programming background. I started off as a kid learning BASIC, and then in high school did some Pascal. College learned C and C++, and then went to grad school, and everything was in Fortran. And that's where I spent a lot of my time, in Fortran. And in about 2008, I started using Python. And I was going to kind of talk a little through my journey and some reasons you might want to consider adding Python to your toolkit when you're reaching out for stuff to do data analysis or to automate things or for whatever. So why I started using Python was back in 2007. Actually, this project started in 2005. I used to work for the Texas Water Development Board, a state agency in Texas, and we were doing coastal estuary modeling. This is a wetland system on the Texas-Louisiana border, and we collected field data for about 3 years, and it's kind of, because I'm actually a computational person, but because I work here, I got to actually go out on the boats and collect data. And as a side note, once you actually collect data, you have a lot less trust in the data your models are using. Especially when you pull out a salinity meter and it's full of barnacles, and you're like, I don't think that measured anything. But anyway, at this time, we were running a couple of hydrodynamic models, which were, number crunching, Fortran, parallelized on MPI. We had a little cluster we built, about 120 nodes or so. And to get all the data, process it, get the input files, we were using Bash, Perl, Oxed, everything. And then all the output and graphs were in Matlab. And that's where I started having issues. Matlab really likes you as long as you do everything in Matlab. Once you start trying to connect Matlab to other things and try and use it as an engine and go and do something else, it breaks horribly. So I needed to run lots of simulations. We were trying to calibrate this model. I was trying to use different data sets. I wanted to automate things. I wanted to run like suites of runs and process it and do stuff and then automatically launch new runs, and couldn't really do that. So what I started doing, well, actually this is exactly what I did. I started Googling MATLAB alternatives. And the top two links were Octave and Python. I did not want to learn another programming language. I was like, I know enough. I don't need to learn another one. Octave, who's heard of Octave? Okay. Octave is close enough to MATLAB that you have a hope that your scripts will work, but then they break horribly in different ways. It's just, and this is back in, it's improved a lot since then, but back in 2007, 2008, it was close but not there. So after about a month of that, I just gave up and said, okay, I'm going to try and learn Python. Let's see how it goes. On a side note, over my career, 3 times I decided I probably should learn Java because that's what everyone is saying we need to learn. And 3 times I got a book on Java, got through about the first 3 pages, and fell asleep. Java's a great language. I know a lot of people do great things in it, but it's also very dense. And you have to do a lot of boilerplate before you actually get anything useful out of it. So Python was much nicer. Print hello world, nice and easy. The reasons I picked it, or the reason I liked it, was I had no background in Python, and I was downloading Python scripts or programs to do different things, and I could understand what they were doing without even knowing the language, because it basically read like you wrote down the logic. It had the scientific libraries I need. It had some very powerful libraries which were very similar to what you could get in MATLAB. It interoperated with everything which I needed in my pipeline. It had some really nice data structures for time series data, which I never knew existed. And just handling dates and times was amazing. And a big part of it was community support. If you actually go to the Scientific Python mailing list and Google my name, for a period from 2008 to 2010 or 11, my names will appear there almost continuously with me asking questions saying, hey guys, how do you do this? And the thing which I found impressive was we were paying for support for MATLAB and TechPlot and Maple and a few other software, and I was getting better support from the community in terms of questions answered and people teaching me how to do things than I was getting when I called our paid support, where we had support contracts. So I started learning Python in the April of 2008. By the fall, I had basically abandoned MATLAB and most of my Perl and all the scripts I had built. I had this little library of scripts to do different kinds of analysis built up. And within a couple of months, I'd kind of just abandoned the whole thing. And it was very easy to transition. So for you guys, why you should consider Python? I was going to kind of give you a high-level overview. I'm not going to go into a lot of details, and I'm going to try and get to some demos at the end, which is always dangerous, but we'll see how that goes. At a very basic level, Python is very popular now. It is, by some estimates, the fourth most popular programming language. Along with R, it is the primary language for data science. Most CS departments are slowly switching over to Python as their primary teaching language. Of course, they still, they're teaching other things, but they're using that as the language to teach in when they're teaching stuff. Engineering departments are slowly starting to move to using Python in some of the classes instead of having that stranglehold of Matlab that is usually in most engineering departments. And pretty much in multiple domains, ArcGIS and TechPlot and various other commercial software like GUI analysis tools or even VTK, PowerView, use Python underneath for automation and scripting or as a way that you can use parts of their library from a scripting environment. So it's pretty popular. I mean, the likelihood of you being able to hire someone or meet someone, know someone who has at least used Python in some fashion is pretty high. It's also easy to teach. It's a simple language in some senses. The other part I like about it is it scales. And I want to talk about scaling in a couple of different ways. The first one is it scales according to your user. When I first learned Python, I used it as a procedural scripting language. I just used it as a replacement for, download this, do this, plot this. Just simple scripts. As I have, it was interesting, my first year or so of coding in Python, I saw my programs go from like 200 lines and smaller and smaller and smaller as I learned better techniques and libraries I could use. And a lot of people now in the business community set up a Python notebook or something with an analysis in it. And you can put a few widgets in and a few variables that a business analyst can change pretty easily. And since, even if you don't know how things work, it reads pretty clearly, even someone who's non-technical can usually tweak something like that. And then as you get more into it, if you're an engineer or scientist, you can actually do some pretty complicated analyses. And then on the other side, if you're going for a software development side, it's got some very powerful tools. And this is the way I like to put it. Easy things are easy. Print is print hello. That's as simple as you can get. Things which are more difficult are sensible. They've got a fairly rational set of defaults, and and hard things are possible. You can write Python is completely object-oriented. It can be used as an imperative scripting language. You can also use it for functional programming and asynchronous programming. You can do complicated things in it. You can write huge systems in it. And it scales on machines. You can use it on your own desktop. You can use it on a distributed system, multi-core system. You can use it on cloud HPC. And there are some really powerful tools to do that. It's a glue language. One of the things which is really nice about it is you can connect to C++, you can connect to Fortran. I think you can also connect to some of the Microsoft family of Sharp tools as well. You can wrap all of those in Python and have a really nice, high-level, easy-to-use API, but calling something in Fortran or C++. And that's essentially what the Python scientific ecosystem is. It's a set of modules. It's very good if you have two different systems written on two different architectures, and you need some way to connect them. It's an amazing glue language. but probably the biggest part of it is the ecosystem. And there's talks out there on why the ecosystem is so big, but at the bottom you have Python. And then I'm going to talk a little bit about some of these things. One of the core parts of Python is this package called NumPy, numerical Python. It is basically kind of the heart data set or data structure underlying the entire Python data and scientific ecosystem. It is highly optimized, it's really fast, it gives you the kind of array manipulation that you get in Matlab. And on top of that, other things have been built. That's kind of the base thing. IPython and Jupyter, and towards the end I'll demonstrate Jupyter Notebook. Those are interfaces that let you interact, do interactive exploration in Python. Around that you have SciPy, which is a set of linear algebra and signal processing, a whole bunch of scientific routines, fast Fourier transforms. And then Matplotlib is a plotting tool. Pandas is a data structure for labeled data. And then built on those, and SymPy is kind of a replacement for symbolic math, like what you do in Mathematica or Maple. Around those you have things like scikit-learn for machine learning, scikit-image for image processing, stats models, PyTables and H5Py for dealing with HDF5 type files. You have network analysis with NetworkX. And then a lot of people are starting to build domain-specific tools on top of that, like AstroPy and BioPython. And there's a whole geospatial stack that's not on this if you want to do GIS and geospatial stuff. The thing which is okay, so one of the things which is pretty different between, say, something like MATLAB or R versus Python is MATLAB and R were primarily a matrix toolkit and a statistical toolkit originally, and they're very good ones for that purpose. And then people realized we need to script this, we need to program this, so a programming language was tacked onto it. And that's why both the MATLAB and the R programming language are not feature complete, and they're not, you hit a wall at some point because they're not well-designed programming languages. With Python, what happened is it happened from the other end. Python was designed as a teaching language in a non-scientific domain. And people started using it for building websites, for scripting, for automating, all this kind of stuff. And then a bunch of scientists who really didn't want to pay for MATLAB licenses anymore started trying to use it to do their science and started building this ecosystem of scientific libraries, but based on a well-designed language. And one of the consequences of that is, like, let's say I do this really nice engineering computation in Python, and now I want to put that on the web. I don't know if any of you, who here has used MATLAB? I'm just picking on it since I used it for so long, but MATLAB actually has a way to put well, I haven't used it recently. So circa 2006, 2007, MATLAB has a way to put your stuff into a GUI or put your stuff into a website. In 2006, 2007, it was very painful and involved several licenses and a lot of pain. With Python, if you build this really nice engineering scientific analysis and you want to put it on the web or you want to put it into a GUI, well, someone over here in the web community has built this web framework. You can just use that. Someone in the desktop GUI community has built this really nice GUI framework. Just plug them both together. You get this benefit from people in other domains building things in Python that you can just connect. And I've used that myself, like scikit-image is an image processing library, and I've used it to process raster data for elevations, which is not what it's for, but it's a grid of data. So it's really powerful to be able to mix and match these different libraries, and because we have this common foundation of NumPy and Pandas, it's really powerful. And that's the thing. So instead of, I've written Fortran code that loops through arrays. That does the double loop through I and j, and you calculate all the quantities and all that kind of stuff. And it's doable. It's horribly painful, especially when you have the indices messed up. What Python gives you is a higher level view with similar computational efficiency. There are some really powerful data structures like pandas, which I'll demonstrate a little bit later, Xarray, and these are, under the hood, they're written in C or Fortran, and they're really fast, but they provide a high-level data structure to put your data in that you can do computations on. And then Dask is a distributed computing framework that it's kind of like Spark and Hadoop, these kind of big data type systems, but it lets you work on data sets that are bigger than your computer can handle, or a data set on a cluster, but with the same kind of nice, easy to use Python framework that you use on a smaller data set. Actually, pandas, I can't remember what it stands for, Python analysis data. So basically there's this guy called Wes McKinney who worked for a New York quant, one of those day trader firms, and he got fed up. So if you guys have used R has a concept of a data frame. So he liked the R data frame, but he liked Python as a language. So he basically ported over those concepts from R into Python and called it pandas, and that has now become the root of the Python data science infrastructure. Previously, we used to talk about NumPy, that numerical Python. That has now become kind of like a low-level package, and pandas is usually what you end up using. And Xarray is for dealing with multidimensional data if you're looking at terrain data or any kind of really big multidimensional data. So there are a couple of issues. What are some of the issues anyone's heard about Python? Anyone? Slow, okay. Any others? Anyone hit this issue? Okay. Short answer, just use Python 3. This has been a big issue in the scientific community over the last 5 years. For those of you who don't know, about 5 years ago, they introduced a new version of Python called Python 3 that fixed some long-standing issues with the family, with the language, and also broke backward compatibility. One of the biggest things is instead of saying print space hello world, it's now print brackets hello world. But there's also some other things they did. It's been a big issue in the scientific community for the last 5 years because big scientific packages that everything else in the scientific ecosystem depend on were Python 2 only. And even a year ago, there was always one package that you needed that was only in Python 2. But as of this year, I went to the Scientific Python conference a few months ago. Pretty much everything is Python 3 compatible. There is also, some people have done some work where you can have the same, there's a couple of packages you need to install, but you can have the same code base that works with Python 2 and 3 if you need to maintain compatibility with 2. But if you do maintain compatibility with 2, you lose out on some of the new features in 3, like asynchronous functions and things like that. But this is no longer an issue. Just use Python 3. If you want more information on that, or if you have old code bases which are in Python 2, come talk to me. Installation's another big problem with Python. It has been forever. It's kind of finally sort of fixed. The issue is Python was not designed as a scientific language. It was designed as a general purpose language. The people who maintain the Python packaging system are not scientists. They're mainly web developers. So the Python packaging system works really well as long as you're working with pure Python packages. Most of these scientific Python packages are a mixture of Python with C and Fortran libraries underneath. And that starts getting into compilers and different compilers for different operating systems and that whole shebang. Getting a good Python installation with all the libraries you need on Mac and Windows, especially Windows, has always been a problem. A couple of companies, a company in Austin called Continuum Analytics, they built this package manager called Anaconda, and you download that, you get all the Python scientific libraries, and if you need a new one, you just say conda install whatever library you need, and you get it. And it works cross-platform. It doesn't require root permission. You know, installs into your local directory. It's just nice. It just works. The speed part, and I'll get to one other thing about the speed. There are a couple of things you can do with the speed on Python. You know, there's a quote, I think by Robert Kern, like premature optimization is the root of all evil. So first of all, find out which part of your code is slow. If you found that out, there are techniques. Cython is a way to put some extra type information into your Python. Cython's like a special way of defining your Python with some extra type declarations, and then it compiles down to a C extension. So you'll get faster speed. Number is a just-in-time compiler, which translates your Python into this LLVM and then uses the LLVM compiler to compile it down to C. And then Theano compiles your Python to use on the GPU. All of these will get you, on small examples, to almost C speeds. On larger code base, they'll get you into an order of magnitude. You'll be about 50% the speed of a big C++ code base. Python is not designed to be as fast as your C or Fortran code. That's not why you're using Python. If you really need that speed, write that part in C or Fortran, put a nice Python wrapper around it, and call it from Python. There's also some really good tools, Dask and IPython Parallel and others. If you've got something which you can parallelize, there are ways to parallelize it to distribute onto multiple systems. So I'm going to say two more things, and then I'm going to try and go to a demo. I've heard this quote said, and I think it's actually pretty true. Python is not the best at anything. If you pick one thing like speed or language design or ability to handle big data or something like that, you can probably find another language that will beat it. The thing is, it's a really good general purpose tool. It's got libraries in so many different areas that you can reach out and use, and using them is really easy. It's also the other part is, I was going to mention this earlier, but I forgot, but almost all the code in the Python, two things which are pretty important to the Python community is documentation and open source with a BSD license. And I'll explain that in a second. So if you look at almost all those packages I mentioned, if you go to their websites, they have detailed help and tutorials and everything. So you can pretty much look for something similar to what you need to do, copy and paste it, and tweak it till you can get it working for your own data set. The other part is Python has a lot of involvement from both industry and academia and universities. So the approach the community has taken to open source is a license which allows anyone to do whatever they want with the code. So there's no viral GPL type stuff. Most of it's BSD or MIT licensed. The last thing I would say is Python's optimized for human productivity, not for machine productivity. The thing I found with Python is in the time it takes, actually even looking at some of the projects I've worked on here, I can develop in Python, find out all my mistakes in my design, and completely rewrite from scratch in a third of the time you could write it the first time in C++ or something else. It's just so easy to tweak and completely re-architect. And in most of the projects I've ever worked on, the first time you're trying to solve the problem or the analysis, you have no idea what you're doing. And once you try to build a solution, you start realizing what the bottlenecks are and where the issues are. Python lends itself very well to quickly reconfiguring on the fly, and also, and this has happened in projects I've worked on, so many people are building so many great tools in Python that halfway through the project, someone will release a tool that you can incorporate, and it would just simplify your work massively. And typically, taking a whole new package and building it into what you're already doing is very difficult in other large code bases. In Python, it works pretty well. So I'm going to try and do a demo. Oh, before I go to the demos, any questions on anything I've said so far? Say that again? So there's two things. When you run, if you write a Python script, it runs, it runs in an interpreter, but the first time you run it, it actually compiles it to a PYC file, which is a compiled file, and then it just runs that. So that happens automatically. The other part is if you want to use something like Cython or Number, which actually creates C modules which don't come back into the Python layer. Oh, like Py2exe? Yeah, so that just wraps it in an exe for convenience, but it embeds the entire Python C library inside your exe file, so you're still actually using Python. So you won't get any speed benefit, it's just the advantage of having one big exe file. So since I'm from Austin, and you guys are here, this is a package I wrote which connects to various weather data sets, and pandas is the thing. I'm just going to run through this. I'm not going to explain it, but these are two weather stations. One is Austin Camp Mabry, and the other one's the Tallulah Airport, I think, which is somewhat near here. I'm going to get the data, and let me hit a plus here. Let's see what that looks like when it comes. So it may take a few seconds to download the data. So, okay, so look, so I've hit these two weather stations and I've asked for snow, and this gives me this pandas data frame which is labeled with a date and has the amount of snow on different days and then some qualifiers. I am going to combine them and drop all the rows where we don't have any data. And let's look what that looks like. Okay, so now I've got a nice little table which says which days have snow, and I am just going to resample this. So if you look here, I'm going to resample it to a decadal period. So 10A is 10 years. I'm going to do the cumulative sum over the 10 years and then just plot it as a bar chart. And that is how Austin and Vicksburg compare snow-wise. Looks like we had a lot of snow before the 70s, and then it got a lot less snow. So that's a very simple example. I'm going to do a more complicated example, and this one I'm stealing from someone else. This is an example which they showed at the conference earlier this year. But this is a software called Data Shader, which is helps you to show extremely large data sets in the web browser in a way that doesn't obscure the data. So we're going to look at this NYC taxi data. It's drop-offs and pick-offs. And while that's loading, if you look, this is a 1.4 gigabyte file. If we have time, there's another 7.2 gigabyte file we can try and load for census data, but we'll see how it goes. So this is loading. It takes about 10 or 20 seconds to load all that data into a pandas data frame. Once you have the data in a pandas data frame, you can do all sorts of slicing and dicing and queries on it. And okay, so it took 24 seconds to load that, and we're doing a tail to look at the end, and it looks you've got about 11 million points in it. Let's just do a very simple plot. And we're only going to take 1,000 of the points of the 11 million, just so see what it looks like. Okay, that's what 1,000 points looks like. Okay, you can't really tell anything from that, and that's only 1,000 of the 11 million. If you plotted all 11 million points, you can kind of tell what it's just going to be this big blob of blue. So we're going to do 10,000 points now, and let's so with 10,000 points, it's just a blob of blue. Okay, let's try 100,000. Okay, this time we set the alpha level to 0.1, so we're trying to, make the points more transparent. Maybe we can see it better. Yeah, it just washes everything out. Okay, so now we're going to use Data Shader, which is the new package they were demoing. So this uses all 11 million points, but it does some fancy stuff to shade it linearly. So this is shading all the points linearly. You can't really see anything because you've got a couple of places where there's only a few pickups or drop-offs, and some places with lots. So when you do a linear shading, it just washes out. So now that we're going to look at a histogram of the data. And so this is what the histogram looks like of the drop-offs and pick-off points. And so we're going to do a log. We're going to do a log plot. We're going to kind of just spread it out a little, and then it looks a little better. So you can kind of see the streets now, which kind of makes sense. People are dropped off and picked up on a street, not at the top of a building. Okay? So that's just another plot of the same thing. They've done some more stuff to spread out the histogram here. They've stretch it out some more. And now, this is the part which is really cool. It's doing all this stuff by manipulating that pandas data frame on the fly. So you can actually do an interactive plot. So this is now an interactive plot of 11 million points. Let's zoom. Oh, I think it doesn't work in full screen. Wait. Okay, there we go. So as I'm zooming in, it's going back to the data set, redoing the histogram, and sending the data back to the browser. And if you notice here, do you see that the points look fuzzy in the middle of New York and kind of clear on the end? Any ideas what that might be? Well, the fuzziness is the GPS coordinates are fuzzy in between the tall buildings. So if you look at the edges, the streets are nicely delineated, but in the middle, it's all fuzzy. And so that's what you can do when you can visualize this data. Previously, it was just a big blob of blue points. And since this is a data frame, let's just go down a little. Okay, now we're doing the same thing, but overlaid with the map. Let's see. So here, now what he's done is, since these are data frames, we can do things like this. We can say, where drops greater than pick, give that one color, and where pickups are more than drop-offs, give it another color. So we're doing this computation on 11 million points and visualizing it, and when I hit enter is when it runs. Okay, that's how long it took. And if you look, the red is getting dropped off and the blue is getting picked up. So people always get dropped off on the north-south and they get picked up on the east-west. I'm not sure why, maybe it's easier. So, and there's more stuff in this example, but I think I'll stop there. Let me see what the last one was. I think the last one just does by hour of day. Let's see if that comes up. So this actually shows you, like they've color-coded it by if it's morning, evening, or when it is. And I don't know my New York geography that well, but supposedly, does anyone know where the airport is in New York? Whichever one's in Manhattan, LaGuardia. Because if you zoom in, you can see that the drop-off zone and the pickup zone at the airport. They did that in the demo. I just don't know where the airport is on this map. So that's what I had. I'm open for questions if anyone has any questions. And in general, if you have any, if you want to use Python in a particular area to do a particular thing, feel free to send me an email. I've been in the ecosystem long enough and know enough of the people from, I know a lot of the people who developed all these different packages, so I can probably point you to the correct package or correct person or tell you what not to do. For example, downloading exe files to install all the Python packages is a horrible thing, and you'll end up having incompatible stuff. So, thank you.